Let's study 10th Standard ICSE Physics, Chapter 3B, Pulleys. A pulley is a simple machine. It may either be a fixed pulley or a movable pulley. A single fixed pulley has its axis of rotation stationary in position. It is attached to this rigid support with the help of the frame. This disc is able to be rotated. There is a string passing through the groove in it. As the string is being pulled downwards, the load can be lifted upwards. The load is a weight, and weight always acts downwards. Now ideally, the effort is equal to the load. That means the mechanical advantage is equal to 1. It's neither a force multiplier nor a speed multiplier. Then what is the use of using a pulley? Well, it can be used to change the direction of the effort to a more convenient direction. If we don't use a pulley, then we'll have to lift the load up by exerting an effort upwards, which is inconvenient. On the other hand, using a fixed pulley, we simply have to pull the string down to lift the load up. We can use our back muscles inside, in fact, the entire weight of a body. Yes, the effort required would be the same, in fact slightly more because there is some friction out here, but it is definitely more comfortable using a pulley. On the other hand, a single movable pulley is one whose axis of rotation is movable. That is, it is not fixed in a position. The string is attached to the rigid support, so when we pull the string up from this end, this entire pulley will move along the string. Here's an example of a single movable pulley works. So this is a rigid support. The length of the string is the same, and this pulley can actually roll on the string as I pull the string upwards. Initially the load was at this height, but when I pull the string up, you can see there is a greater length of string on this side and a lesser length here because the pulley disc has rolled. It has been lifted. In fact, the height of the load has increased till here. So this is how the pulley can be used by a person to pull a load. The benefit of a single fixed pulley is that it is a force multiplier. A less effort is required to lift the same load. For example, if the load is of 10 Newton, then the effort required is perhaps just 5 Newton. In a single fixed pulley, the effort required would have been the same. But here, only half the effort is required. Yes, the direction of the effort is upwards, which is a bit inconvenient, but we can overcome this. But let's understand how is the effort required halved. Here we see that there are two strands of the string supporting the load. There are two tension forces supporting the load. So we can say that the total load is equal to 2 times the tension force, whereas the effort is always equal to 1 time the tension force because it is only on the RHS, that is the right hand side. So substituting, we see that effort is half of the load. That means mechanical advantage, which is nothing but load upon effort, comes up to be 2. This means that the effort required to lift the load is half of the load. But as you know, force multipliers will slow down your speed. There is always a sacrifice which has to be made. So the catch here is, even though the effort required will be half, but the displacement of the load will be far less than the displacement of the effort. What this means is, if you have lifted the string by, let's say, 2 meters, however, the load will be lifted by just 1 meter. So the displacement of the effort is double the displacement of the load, which may be fine if you simply wish to apply less effort to lift the load. So the velocity ratio is also 2, assuming that the efficiency is 100%. Mechanical advantage and velocity ratio both are 2 each. But we know that practically that's not possible because efficiency is never 100%. Now, if we want the direction of effort also to be in a convenient direction, then we can use a combination of the movable pulley and the fixed pulley. The movable pulley will give us that mechanical advantage, and the fixed pulley will change the direction of effort. So here again, you pull the string down, and from here, this pulley as well as the load both of them will be lifted up. Half the effort will be required, so its mechanical advantage is totally 2. But again, the displacement of the effort will need to be double the displacement of the load. So you pull the string down by 10 meters, but the load will be lifted by only 5 meters. Next, let's talk about a combination of pulleys. There are 2 ways to use multiple pulleys together to get various mechanical advantages for various purposes. One way is using one fixed pulley and many movable pulleys. Now, while drawing this diagram, it is compulsory that the strings have to be drawn with a ruler. They should all look parallel to each other. For the pulleys, you must use a pro circle. A rounder would be too time consuming. And make sure that the strings are tangential. So first you should draw the circles and then draw the strings. See how this string passes through this groove and then it is attached to the pulley B right in the center along the axis. Similarly, this is attached to the pulley C right in the center. These strings should not be diagonal. Again, this is tangential to both the circles and it passes through the groove and comes down. So if you pull the string down from here, you are actually pulling pulley C, due to which you are pulling pulley B, due to which you are pulling pulley A up, and finally, indirectly, when you pull the string down, you are lifting the load up. Labelings of the tension forces are also necessary: T1, T2s, T3s, and here T3. Now it can be derived that the effort is just 1/8 of the load, but the derivation isn't there. We can simply remember a formula to calculate the mechanical advantage of such a system, and that formula is that mechanical advantage is equal to 2 raised to n, where n is the number of movable pulleys. Now here, the number of movable pulleys is 3. Don't count this is a fixed pulley. So 2 raised to 3 is 8. So mechanical advantage is 8. That means the load will be 8 times the effort. So if the load is, let's say, 8 Newton, the effort required will be just 1 Newton. So that makes our work so easy. But again, there is a catch. This means that the velocity or the displacement of the effort, if the load has to be lifted by 1 meter, the effort needs to move by 8 meters. So the speed decreases. The velocity ratio is also 8 in this case. Now practically, the mechanical advantage won't exactly be 8, it will be slightly less than that because of 2 reasons. First of all, the pulleys and the strings are not weightless, they have a weight. So you are not just lifting the load, you are lifting the weight of these movable pulleys as well as the strings. Now, no matter how light they may be, but still that reduces the efficiency. And the second issue here is obviously the friction between the bearings of the pulley. Now another method of arranging the pulleys is using several pulleys in 2 blocks, which is called the block and tackle system. It looks like this. Now these diagrams are very important, and understand how to draw them. If the number of pulleys are odd, let's say 5, then remember the upper block will have 3 pulleys and the lower block will have 2. But if the number of pulleys is 4, then 2 and 2 each. So the lower block can never have more pulleys than the upper block. Let's see how to draw this one. Again, if the number of pulleys is odd, then start drawing the string from the lower block and use a ruler only. Remember, the string should be tangential to the circles. It should not just intersect the circle. First, we should always draw the pulleys, and preferably with a pro circle. See how the first pulley here and the last pulley here are the largest. The diameter is greatest. Then the size of the pulley decreases and the innermost is the smallest. This way we can be sure that these strings don't touch each other, which is very necessary. So once we draw these pulleys, they have a single frame, so that is one block. This has a second frame, so that is the second block. This upper block is fixed. The lower block is movable. So let's start with the string from the lower hook. It goes around this, goes straight, goes around this, straight, and then goes around this, and the effort finally. Once again, if the strings are not drawn with a ruler, we will get 0 in the exam for the diagram. Show all the arrows showing the tension forces. Tension forces are always upwards. And the effort is downwards in this case. So when you pull the effort down, the load is lifted up. Now here we see that the effort will be equal to T, but the load is being supported by 5 strands of the string. So the load is equal to 5T. That means the effort is just 1/5 of the load. To lift 10 kgf, you will require an effort of just 2 kgf. The mechanical advantage is 5. Interestingly, that is equal to the number of total pulleys used here, fixed as well as pulleys. So you can guess that in this system, the mechanical advantage will be 4. So to lift a 10 kgf weight, we will just have to apply an effort of 2.5 kgf. Again, note how these two circles are big and these are small. And since the number of pulleys is even, this time start the string from the upper hook. Use ruler and make sure that the strings are tangential to the circle. Show the directions of T as well. If you start from a wrong hook and you can try to draw it, you won't get it right because we want the effort to be downwards, not upwards. We want it to be in a convenient direction. So here the mechanical advantage is 4. But there is a catch. If you move the effort by 4 meters downwards, the load will be lifted by just 1 meter. So it slows you down. But that's okay. At least you're able to lift heavy loads easily with less effort. So these are all force multipliers. Now if we were to start drawing the string from the other hook, then we would realize that the effort will have to be pulled upwards. In such a diagram, the mechanical advantage won't be 4. In this case, it will become 5 because it will be supported by 1 additional tension. Similarly here, if the effort was in upward direction, then the mechanical advantage would be 5 plus 1, 6. So we will get more mechanical advantage, but we don't prefer it because then the effort will need to be applied in the upward direction, which is very inconvenient. We prefer effort being applied in the downward direction. So we'll pull this down and the load is lifted up. And not only the load, the entire lower block is lifted up. So imagine the lower block was suppose here with the load. And as you pull the string down, the entire lower block with the load is pulled upwards. The upper block remains fixed. That doesn't move. That just rotates. So remember, in the block and tackle system, mechanical advantage or velocity ratio is equal to the number of pulleys. That is assuming that the effort is downwards. And of course, the efficiency is 100%. That's the assumption we make in all these ideal cases. Now remember that even though it's a force multiplier, it doesn't mean that we are gaining energy. Yes, it's true that if you apply just 2.5 kgf of force, you can lift a 10 kgf weight upwards. But the amount of energy required is the same as it would have if you lift it with your bare hands without any pulley. In fact, this would require slightly more energy because there is a loss of energy due to friction. Now, to mathematically prove that the energy output and energy input is the same, let's consider this. What is the work done by the effort? Work done is effort into distance moved by the effort. Let the effort be, let's say, 2.5 kgf. And the displacement, let that be 4 meters. N is the number of pulleys, that's 4, and let the displacement of the load be 1 meter. So 4 into 1b is 4 meters. So total effort, total energy or work done is 4 into 2.5, 10 units. Now let's calculate the work done on the load. That is load into displacement of load. Load, if you remember, was 10 kgf. We lifted a load of 10 kgf. But it did not rise by 4 meters, it rose by just 1 meter. So into 1, that is equal to 10 units again. So you see NED is equal to NED, or numerically speaking 10 and 10. This proves that there is no gain in energy.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.